So let's begin our third day. Unfortunately, I have to tell you that the last paper by Professor Alexander Belinki will not be presented because he's in the States and he's sick. So he asked to excuse him. He will not be able to present the paper. But now we have the paper. There is a talk by Boris Myrkin, Professor Boris Myrkin. I would like to say a few words about him, just a couple of sentences. And Boris is working in HSE University, very well known as a world specialist in data analysis and many other fields. And I can tell only that his books, his papers, his articles were by these publications, many people were taught by these publications, especially I can tell about myself. So, his influence to data analysis, to many fields in social choice, etc., is very, very high. So, Boris, floor is yours. Please go ahead.
Oh, thank you very much. So I'm switching on my presentation. Let me do slideshow.
Boris, make it full screen. Yes.
So this is, I also want to, like several previous presenters, I would like to thank Professor Aleskera for inviting me. And my gratitude extends further. I thank him for inviting Professor Francisco Carvalho from Brazil to our lab past year. And this paper that I am presenting is I would say, fruit of that visit by Professor Carvalho. So we joined forces, and this work has been published. Here is the address on web, and I'm sure if you put down on Carvalho, Myrkin, and something like k-means, you will find it immediately. So the plan of my talk is as follows. First, I'm going to remind you of k-means. Then I'm going to describe my own considerations related to extending this to a complementary criterion. Then I will describe the interval data that our team has produced. Then extension of this k-means versions with the complementary criterion to the interval data, and then a few words of our computational results and so forth. So I hope that it would take about 1 hour of time. So this is about the k-means criterion. On the left, you can see a number of black dots that represent objects, red stars representing centers of clusters. So this k-means clustering operates with a partition, each of the set of objects in clusters. Each cluster has a center. So this, the criterion of this method is the sum of distances from each object to the center of its cluster. So this is the sum over clusters, and within a cluster is the sum of distances from all objects in the cluster to the center. So CK is the center of cluster C. What is the distance? Distance is the Euclidean squared distance. So it's not a metric, it's just squared Euclidean distance. And here I show an example. If we have two vectors, X and Y, then we take the difference of them, and then we sum the squares of the components of the difference. This is the distance. So this is the criterion, and the method operates in alternatingly minimizing this criterion. So given C, so we have two groups of variables, C, the centers, S, the partition. So given C centers, we take the minimum distances. So for every I, we select that center to which the distance is the minimum. And in this way, we assign all entities to their centers, after which we produce center update. So in each cluster, we compute the centers, the means, explaining the name of the method. So this is just to remind you of the method. Now, this method can be, so this criterion, the D, is basically the least squares criterion for this bilinear model. So Y on the left are given values, C are the centers, K are clusters, and Z are binary vectors of belongingness for cluster K. So that the values of these vectors Z I K are 1 if I belongs to K, and 0 if I doesn't belong. And this model can be expressed in matrix format as a matrix factorization, and currently this is the most popular format for various models in data analysis. So here I give a kind of present a similarity to principal component analysis. It's the very same model.
Boris, sorry, can you show the previous screen?
So here what we have, the sum here.
What is V there?
V is the variable, it's a feature.
Okay.
I is object.
Yeah.
So we have a matrix of objects, and the values for a number of features. V are the features.
Okay, yeah, I understand.
So for every feature, the value of Y is approximated by CK, by the value of Y over the center. What center? That one center to which I belongs. And this is why the sum here is basically a kind of, how to say, it's purely formal, because in fact, ZIK is equal to 1 only for 1K. So all the other Z are zeros.
Okay, yes.
And this allows to have this simple model as a linear, is a multiplication of the incidence matrix. So Z is the incidence matrix of clusters. So that the size of it is the objects, the number of objects over the number of clusters. So every column on Z is just a binary vector. The unities stand for members of cluster, of cluster K. K is the column. And C is a matrix of centers. And we minimize the errors. And this is the nature of this method. So this is the criterion. And I make a very simple I would call it arithmetic, but the English says that it is not arithmetic because there are numbers here. So it's algebraic transformation that allows me. So the first item here, maybe you are right. I should. Usually I kind of swallow this, and I need to maybe to tell this a little bit, kind of slower, make my pace less formal. So what we are having here. So this is just that criterion that expresses the sum of distances from eyes to the centers, summed over all features. V are features. So now I take the Newton's binomial, and I see here that the first component, the first item here is the sum of it is just the sum of all entries, all data entries squared. So they are squared, and this sum is does not depend on any partition. It's a constant, and it is a data scatter, the quadratic data scatter. And the criterion D we want to minimize, and we get a complementary item here that I denote by letter F. And this equation gives me the Pythagorean decomposition of the data scatter into the explained part and unexplained part. This equation is rather easy to derive, and it is known for quite a while in ANOVA, analysis of variance. In analysis of variance, the partition is given. So it has never been interpreted as a criterion to maximize, because S is given in ANOVA. And in our case, S is a partition that we want to find. And so we can take a closer look at this decomposition, that we want to minimize the part on the right. That means we want to maximize the part in the middle, this criterion F. So what is this criterion is? It's a sum of individual cluster contributions. So each cluster K gives a contribution. It's a part explained by the partition, and it is very simple. It's the number of elements in the cluster and multiplied by the square distance from the center to 0, to the origin. This is what we want to maximize. And this is basically so we minimize, in K means we minimize the distance to the centers. And here we maximize just the contribution, the summary contributions of clusters. And there is a catch here. The distances don't depend on the origin. And the inner products, CK multiplied by CK, do depend on the product, on the origin. So whenever we shift the origin, the D remains the same, and F changes. But what is important, that the change of F does not depend on C. Oh, sorry, does not depend on the partition. Change in F does not depend on partition, and so you can maximize this, getting the same result if you do it globally, independently of the choice of A. But when we look at these criterion, that obviously again, I'm sorry, I'm telling you independently of choice of C, I want to say independently on the choice of the origin. So now I'm going to explore this complementary criterion. This is what it wants. It wants to maximize simultaneously the number of elements in clusters and their distance to the origin. So this is what I find it very appealing. Geometrically, the meaning of the complementary criterion is quite appealing. So what we want is to find the anomalous clusters, the most populous, containing as many elements as possible. It's I published this quite a while ago, and I saw no one picked it up. Some of my methods that I proposed a while ago have been reinvented with no credit given to me. And this method has never been reinvented, and I don't know what to think of this. So unfortunately, I never tried to maximize this criterion simultaneously by finding clusters simultaneously. It's probably lack of courage. Or maybe just I find the extraction of clusters one by one very attractive. So what I'm doing, I take the most anomalous cluster first, remove it. Among the rest, I find the most anomalous again, and so forth. So this is the method of anomalous cluster. And to do it, I put the origin into the grand mean. Grand mean is the average of is the total average over the data table. And this is how this method operates. So how I find the very first cluster. So this big square denotes the origin. It is here referred to as the reference point. So what I need is finding the cluster, anomalous cluster, a populous anomalous cluster. So this method operates in this way. I find the farthest away entity. So I take every object, measure the distance, the square distance to the center, and I take that one for which the distance is the largest. This is the center of my cluster. Now I start the k-means iterations. So I take every entity and take its distance to the center and to this the center of the cluster. And I assign this entity to either the global center or to the cluster, depending which distance is smaller. So this is what I'm doing. Instead of taking the sum, I take just one item from the sum and I maximize it. This is my criterion. I want to maximize, and this is what I'm doing. Iteratively, like in k-means, that so I take the initial center, the object farthest away from 0. Then I do cluster update for every I assign it to my cluster if its distance to C is smaller than to the 0. And after this, I compute the mean in this S and start the iteration again if the new C is different from the previous C. This is how this method operates. And it is almost the same as k-means, except that the number of clusters here, 2. And then the center of the main body never changes, never changes. It is always at 0, does not change. And there is a natural initialization here from the entity which is the farthest away. In k-means, they usually don't know from which C to start, so they usually take the random starts, randomly selected entities as the centers. I just was teaching this method in my class on basic data analysis, and I said to my students that this method was once stolen from me, and the Americans called it very nicely gene shaving method. So you shave the data from a bubble, but because they did change the 0 every iteration, so the method did not work, and in a couple of years they stopped using it. And a student of mine took his notebook and wrote the gene shaving and found an interesting, the author never gave any credit to me. And he found just a couple of days ago, a couple of weeks ago, mentioning of my name that it was me who invented gene shaving. Now, with this method, if I can find the anomalous cluster, that's easy. So I remove it. And with the rest of the data, I do the same. I find next anomalous cluster. And after I've classified all the entities into those anomalous clusters, I take the largest, the k largest clusters, take their centers as the beginning, as the starting point of the k-means. So this I call intelligent k-means. So intelligent k-means is a k-means in which the initial centers are found in this anomalous clustering process. I had a PhD student back in London. Probably he defended his thesis in 2010. So he did a quite extensive experimentation with many different proposals. And this method, unfortunately, did not show quite good results with the number of clusters. In k-means, you don't know where to find the k, the number of clusters. So this method was not good in determining the number of clusters. But with respect to the cluster recovery, it was the best. It was superior to all the others in those experimentations. And so to show how it works, I apply it to a famous dataset iris, which is 150 specimen of the flower iris with 4 measurements. And so it gets after 6 iterations. So the very first center is an entity number 132, is far away from 0. Then the next iteration, it gets 27, and the center gets closer to 0. So now it gets 47 entities closer to this C1. And again, the center of this gets even closer to 0. So out of 150, in the end, 60 entities belong to the anomalous cluster with this center. By continuing this process iteratively, as I explained to you, we get the next cluster of 50 entities, 31 entities, And this basically exhausts, takes almost all, it's 141 objects out of 150. So all the rest are more or less anomalous, just singletons. And what is nice here, that these contributions to the data scatter are shown here in the percentage to the data scatter. And we can see that the method that I explained to you, the anomalous clustering method, is not optimal. On the first step, it gives you 34%. And on the next step, it gives you 51%. So if it was global, then the anomalous cluster 2 would you get in the first step. But you cannot do this because this method starts from the furthest away entity, and it should start from something else. So this is yet another unexplored possibility is of finding the starting point for anomalous clustering. And this is now what that we have this sequence of the contributions. We have to decide how many clusters we want. And if we judge over the number of elements, then you should finish at 3 clusters, 60, 50, 31. But if you judge over the contribution, this is what you maximize, then you need only 2 clusters, because cluster number 3 gets a real big drop. So this is another issue that I never explored experimentally, is the stopping point at this process. How many clusters do we want indeed? And I cannot find a student for a PhD studentship because nowadays our students are not interested in dissertations. They want a job in industries. And I understand they're absolutely right, because the salaries in academia are much more modest. Okay. Now I want to, since I proposed this quite a while ago, I applied this approach to many other, to many environments. And I can see that the most successful is the most recent approach, is a recent research undertaking my former student, Dr. Susana Di Nascimento in Portugal. It's about the analysis of the oceanic upwelling patterns. So this is a map of the ocean. This white thing is the coast. It's Portugal, on the very west of Europe. The white thing is the Portugal. The blue is cold. The red is hot. These are the temperatures of the ocean, or the Atlantic Ocean, of coast of Portugal. Now, some area here is what they call upwelling. Upwelling is a very interesting physical phenomenon in the ocean. It's basically a tube, a long tube, horizontal tube that rotates around its axis. So it's about 10-meter diameter of the tube is 10 meters, and the length is 100 kilometers. And it rotates and brings fresh water from the surface down 5 to 10 meters down, and brings that water from the 5 to 10 meters from the ocean to the surface. And somehow they say plankton or something, I don't know. Anyway, the fish likes this and it flocks there, and it's very useful for the fish industries. So they basically, it's a place where you can that fish. So it's very useful economically. Unfortunately, this phenomenon has not been formalized as yet. So the only way to discover it is an intuition of an oceanographer, of a specialist. They take a pencil and draw a boundary according to their understanding, and they say, oh, this is this colder part, a very sophisticated boundary. This is the upwelling. And with our algorithm, this anomalous part, that it draws real sophisticated boundaries, not because of the boundaries, because we take pixels and based on their temperature. So it reproduces the pictures by oceanographers with a very great precision. 90% of our reconstructions coincide exactly with the drawings by oceanographers. So at this moment, we got a little bit further. So we analyzed the data for 16 years, and our anomalous clusters do represent upwellings, and we found that there are some stability periods in there. And we checked with the other data. So now what we are doing, we are exploring the relation between our discovered stability periods and the winds, the speeds and the directions of the winds in the ocean. This is the work in progress by now. Susanna, she can prove that this method of the anomalous clustering, she also applied a number of the other methods, gives the most consistent results. This is again, I'd say, her work to be published. So now, so this was, I said, in defense of the method. Now, let us move on to the subject of this talk, about the interval data. So this is a mushroom, what we call in Russia, I guess, sirayeshka. It is not from Russia, it is from California. So individual mushroom can be measured. The diameter of the pileus, it's a Roman, pileus is 80 millimeters, and the length of the stipe, I guess here is about 50 millimeters. But nobody analyzes mushrooms as individuals. They analyze mushrooms over categories, over taxa, of their biological taxa, like here. So this belongs to Mycena californiensis, californiensis, and the pileus in Mycena is between 70 millimeter and 200 millimeters. So now it is not a value anymore, it's an interval. To be honest, I would consider that we should take not just an interval, we should take the distribution. But this is probably the issue for my future research. The distributions have been analyzed. So there are some interesting mathematical approaches there, but we are doing now just the intervals. So this is from where intervals are taken, from the categories. So we were able So they claim that there are 588 categories of mushrooms in California. And California is a pretty big state. It's about 35 million inhabitants. So one can believe that there are as many types of mushroom. They are called fungi in Roman, in Latin. Their nomenclature is described in Latin language. And out of these 588 categories, we could find the data for 180 categories. And we have this data set, about 5 features. So the spores, the length and the width of the spore, and the speleus and stipe, a length and width of stipe. So 5 features of 180 categories. This is what we have. And what we like in there, that out of these 180 categories, there are bigger, larger classes, like this agaricus, a class containing 26 categories out of 180, or boletus, 19 categories, and so forth. So we take these larger biologically defined classes of the biological taxonomy as our ground truth. I couldn't find this ground truth. So for the computational experiments, it's very important that we don't invent them. This is the biological taxonomy. So we take either 3 largest classes, or 4 of them, or 5. And this gives us the data set. So if you have only 3, then 26 plus 19 plus 16, 61 entities form our data set. If we add 1 more, then it will give us 75 entities in a data set with 4 ground truth classes. So this is a very good data, natural data, real world data that can be used for computational experiments. Another data set, and you can imagine why it is Brazilian. It's a Brazilian research production. So for every team of scientists, they count the number of efforts on 33 categories. Publication in a national journal, or in international journal, or just a paper in a seminar, or a conference abstract published, or a bachelor degree obtained, or special training, even if not completed. And the special training completed is just the previous item. So, or if you produced an artwork, still it is in the count. So they count the numbers of production over these 33 items and sum them, well, and compute the average output of every of these 33 items or features. So in this way, there is a data set which is available on web of 5,620 entities. This table is available. So we did further on, we aggregated this. Over research areas. So these research areas have been defined, not by, again, in this file. So this data is available. We just took the aggregation instead of average, we took medians as a kind of more robust estimates. And in this way, we got 76 research areas. Further on, we removed all the features that had 0 as the lower boundary on the corresponding interval. So again, we defined 76 categories, and we took from minimum to maximum of their values, the interval, and we removed all those features at which we had 0 as the
Boris,
lower boundary.
sorry, but how did you define these 76 categories?
How we define what?
76 categories. Where
It is
they
defined.
given?
It was given.
They were given. Okay.
These areas have it's examples of the areas like technologia. They were assigned to each of the 5,000 rows. So this have been defined. We just aggregated. We took the aggregates over this area that have been assigned in this data table. So it's not us. It was given. This area, these titles, they have been assigned.
Okay, thanks.
It is a little bit more, how to say, complicated because it is the assignment was 2-level. The larger area, they call it grounder. I don't remember the Portuguese. In Brazil, they use the Portuguese language or the Brazilian version of the Portuguese language. But that doesn't much matter. Anyway, we did not invent anything here. We just used the categories that have been assigned in this. And if you see here, for instance, you can say, I said, we removed the 0 where we had a 0 on the left boundary. Here it is not 0. It is about 500ths, just to kind of to be able to show it in one slide. I removed the decimals starting from 0, so that I could show you the intervals, like here, from 3/10, from 3.5. So these intervals are basically, I show them just to show you how arbitrary they are. And again, here is 16 dot, so I just removed other digits. And unfortunately, I cannot translate these Portuguese names that remain out of this 33 items. But anyway, so we have 8 classes, also predefined. It's bigger, the larger research areas, like biology. It's Portuguese here. Probably ciencias biológicas. Okay, I don't know. It's social sciences, engineering. Let me understand. I should have here. Oh, yeah, I have. Yeah. So these are the numbers. So out of these 76 sub areas, 13 belongs to biology. like for instance, agriculture or some 13 belongs to social sciences and so forth. So these are 5 most numerous classes out of 8. So that we take, again, our ground truth. We take the first 3 classes, which is 39 objects only, or 4 classes, which is 49 objects, or all 5. So 3, 4, or 5 classes as ground truth for our experimentation. So what is the experimentation? We apply an algorithm. We know the number of clusters, say 3, and we compare the partitions that we obtained with this partition in 3 different classes: biology, social science, and engineering. This is what we do. So now I'm moving further away to the extension of k-means clustering to interval data. We follow here to the recent work by Francisco Carvalho and his collaborator. And I can see nothing specifically interesting here. So again, we sum over clusters. Within the cluster, we sum over all objects. And we sum over all features. And now what we have? We have 2 boundaries, first boundary and second boundary. So we take differences between the first boundaries and the second boundaries in the intervals. And we have weights. Weights that are found adaptively, that are found in the process of computations. So the weights, so we optimize this over weights. And there is a beta here to make the computation more kind of flexible. It is a parameter adjusting between the distance and the features, something like this. People use it starting from the classical works by fuzzy clustering people. So I decided to keep it here as well. Why should we remove anything that people are using? So here it is just, so they given the interval data, left and right boundaries, the number of clusters and the parameter beta. We want to find the partition, the cluster centers, and the feature weights. So basically weight of the left boundary and the right boundary. This is what we want. And there is no much invention here except for the constraints. Oh, this is the Rodriguez. I don't remember the name. So in the original paper by Rodriguez and Carvalho, it was no beta. So we introduced it, but it was a constraint, normalizing constraint over the weights in a very unusual form. So the product of all the weights is to be unity. So some of them must be larger than unity because there are so many items in the product. And those that have, it is larger than unity. So they probably are most contributing to the criterion that we want to minimize. And we also use the heuristical condition. The first person who did it, it was a Chinese team published in 2004.
Boris, sorry, can you explain, is there some kind of, you see, meaning behind this weights, not normalization, but the sum of the multiplication of weights should be, multiplication of weights should be give 1 or, next slide, next slide.
I asked Francisco, he gave me answers that I cannot understand.
Okay.
I looked at his papers. I found no answer. This is yet to be, but at least this is an innovation. He introduced it, and it is nice. The derivative of it works perfectly, and so it should be further explored. So this is a controversial item. I agree, and I cannot answer this question.
Okay.
So the method works exactly like k-means, alternating minimization. So given S and C, partition and centers, you find weights. The formulas are quite complicated, but they can be derived from the first order optimality condition. So we take the derivative of this over W and equalize it to 0, and it can be solved analytically. So next, given S and W, you find optimal centers. Given weights and centers, you find a partition S. And for this, it's basically, this is the, again, it's based on the minimum distance. So it's basically the optimal S that you found. So now about the experimentations that we did. So what the algorithms involved? The IKM is the method, which is the extension of the method proposed by Rodriguez and Carvalho quite recently in a very good journal of the first quarter journal, Expert Systems and Applications. So we take this method involving various options for feature weighting. No feature weighting, optimal feature weighting cluster specific, conventional feature weighting. It's just that we use these one formulas. So these 5 different options for this algorithm. Then the same algorithm in which the initial S is found with the anomalous clustering. The number of clusters is known, so we take the largest clusters, largest anomalous clusters, take their centers, and apply AKM. And in anomalous clustering and IKM, we can use different weighting schemes because these are 2 independent parts, and we can use different weighting schemes. And to be comprehensive, I included also the ordinary k-means. When I consider this data as ordinary data, so instead of intervals, I take 2 features. One left boundary value, the other feature right boundary value. So I double the number of features, and in this way I get just the ordinary data set, and I apply ordinary k-means with feature weighting. It's this criterion with feature weightings. Now, the protocol of the experiments is this. We take, as I said, we have 6 cases of data. Fungi or research production, And in each, we take 3 cluster partition, 4 clusters partition, 5 clusters partition. So there are 6 data sets for the experimentation. Now, how we apply IKM? We take 100 random initializations. Beta is adjusted. I don't want to explain you how it is. It's optimally adjusted based on a big experimentation. And out of this 100 random initialization, the best clever recovery result is recorded. I want to point out that to record this, we need to know the clusters. When we do clustering, usually in practical situations, we don't know clusters. Here, to determine this, we must know the clusters to measure the cluster recovery. The ordinary k-means, we don't apply optimal because there are no optimality here. The same way, again, the best cluster recovery result. ICM, now our method with the anomalous clustering is done only once because anomalous clustering produces k clusters, k anomalous clusters. You start from them, you get the result. So it's only once computed, and that's it. And the feature weighting, as I said, so these are the protocols. Now, how we measure the quality of the cluster recovery? So we have a ground truth partition, and we have the algorithm partition. And we take what is referred to as ARI. It's adjusted rand index. It's basically at the distance between partitions that are introduced in 69, normalized to be 0 at the stochastic independence and unity when partitions coincide. This is, we are not original, it's standard. We also measure normalized mutual entropy, but since results are very similar, so I don't mention it here. So it's basically the similarity between clusters. And to be honest, we know that it is unity when A is equal to B. We know that it can be negative when the partitions are dual to each other. This I can tell if a question would be raised. But we don't know what is the minimum of this value. So I could reach -1/10, but I don't know if say -1/2 reachable or not. I don't know, and nobody knows. So here are the results. The smaller the number of clusters, the better recovery. Feature weighting does improve the results. Oh, sorry, my mistake. The best results for IKM and ordinary k-means are comparable. So that basically raises an issue. Do we need IKM at all? Or we can apply the k-means just to the double data. Now, when we apply the anomalous clustering, then there is no need to have different weighting feature schemes. The better results are obtained when both weightings are the same. And now the main result. that the anomalous clustering in general gives results that are not better than the best results by IKM, but it is always within 1/4 of the standard deviation from the maximum. So basically, we consider that a good result if it is within 1 standard deviation. The standard deviation, oh, unfortunately, I forgot, is usually quite low. So this tells us that using anomalous clustering is advisable. Because, as I said, in usual situation, you don't know clustering. So there is a warranty here that what you get may be not the best clustering, but it is a decent clustering results. So this is the first part of my conclusion, that anomalous clusters are worth to apply here when no prior information is given. The issue for theoretical and practical investigation is what about the cluster structures at which this method is adequate. I mean, the anomalous clustering is adequate. This refers to a major issue. How can we measure the complexity of the data? And I know that in this laboratory, there is a person who has been doing the analysis of complexity of the data for quite a while. Probably we should listen to him, what he could say about this. It's Alexander Lubchinsky. With this, I finish my talk. Thank you very much.
Thank you very much, Boris. It's very interesting. Very interesting. Boris, okay, sorry. So questions, remarks, comments, please, go ahead.
Okay.
Sorry?
I don't know how can I return to the
no, don't return to the main screen because maybe somebody will ask question when we need some slides. Boris, I have a question. You see, you made this very biological clustering, I mean, of fungi. Let me pronounce it in Latin way. Okay. Did you compare it with the biological, let's say, structure by some kind of biological basis, you see?
Biological what?
Biological, not logical, biological basis. I mean,
basis, okay.
This group of fungi, this is another group of fungi, etc. Did you compare them in this way? I mean, after you did this very clustering.
What comparison do you mean? I just
for instance, by families of fungi, you see, by biological.
So you basically ask, maybe our clusters better suitable to the biology than the current taxonomy. This is what.
Yeah, yeah, that is the reason.
It never ever occurred to us. Maybe a good idea. Maybe you see the biologists. Why we cannot do this, in my view, the biologists have so many differences in their views of the taxonomy that I think we can always find somebody who would be better inclined to our reconstructions. There are so many differences in opinion. Yeah.
Well, yeah, that's right. You see, I agree with you concerning this variety of views, variety of classifications in biology itself. But maybe to compare this with compare, or maybe to show it to biologists, and maybe it will be possible to
A good
find
point.
some deeper understanding of this situation. You see,
It's a very good point. Yeah, that's a very good point. Do we have a biology department in our institution?
I think so. Yes, I think so. They opened a few years ago, 4 years ago, something like that. If you wish, I think I know the head of the department. If I'm not confused, I can.
Okay, we will.
talk to
Thank you very much. This we can elaborate further.
Okay, good. Some other questions, please, remarks. Boris, then I have another question, you see, which this very, I don't exactly know this terminology which you used. I mean, this very further filtration of anomalous clusters, sorry. You see, you first this filters these anomalous clusters, and my question is the following: to which it should really make a much faster the work of algorithm. Is it correct?
Oh yes, it is. We have a paper on agglomerative clustering. In a very good journal, maybe pattern recognition, I can remember. Makarenkov, Renato Amorim, my former student in Britain, and myself, about usage of this anomalous clustering as part of the agglomerative schema. And we showed that it was much faster indeed, much faster.
Yeah, much faster, yes, I could imagine, yeah. Okay, thank you very much. Other questions, comments, remarks, please go ahead. No, Boris, thank you very much indeed. And I would like to tell that at 4 o'clock we have the next talk by Vashevnik and Jangirov. Okay, thank you very much. See you later.
Я сразу хочу вас предупредить, что сегодня последнего доклада, который был назначен на 6 часов, его не будет. Профессор Беленький заболел, значит, и поэтому сейчас как бы последний доклад. И мне очень приятно представить наших коллег из Сбера. Значит, прошу прощения, Джангир Джангиров, первый вице-президент Сбера, и Андрей Вashevnik, извините, Андрей, я вашу должность не знаю, оба выпускники Мехмата МГУ, РЭШ, и сделавшие вот такие замечательные работы именно в части, так сказать, как раз принятия решений вот в финансовых приложениях. Пожалуйста, floor is yours. I'm sorry, I automatically see in Russian. So it is my pleasure to introduce today's speakers, Jangir Jangirov and Andrei Vashevnik from Sber companies, from Sberbank, the greatest bank of Russia. And they both are graduated from Moscow State University, Lomonosov Moscow State University Mathematical Department and Russian Economic School, and did a lot of serious things in mathematical applications, mathematical models in finance. Please, floor is yours.
Thank you, Fuad Tagievich, and good afternoon, everyone. I hope everything is fine with the sound. If something is wrong, please let us know. So today, let me quickly introduce ourselves in like more details. I work in Sber as a chief risk officer, and Andrei is the head of model validation. So model risk is one of the has become one of the most important risks for SBER. We have currently almost 2,000 models in the use. So Andrei and his team are responsible for validation of those models. And why we do validation, because we're very sensitive to the quality of the model. So if anything is wrong with the model at the inception or during the work of the model, then Andrei and his team shall alert, and then we do something about it. So today we're gonna talk not really about model validation, or not only about model validation, but rather about LLM, large language models, and about how they are used in business practices, and what we do about their quality. I will have to go like in 20 minutes, so we'll start together, but then Andrei will continue alone. So let's start with a quick introduction on what LLMs are. So basically, to build large language model, you have to have like very large set of data. It's we're talking about terabytes of text, which is quite difficult even to collect that amount of data. But not only that, you have to build also model architecture. And here in the middle of the slide, you see an example of like simplified example of the model architecture for basic LLM. And then you need to have like immense computing power. You have to have like GPUs, which are quite, by the way, expensive today. You have to have the thousands of them in order to build LLM from scratch. In case you design your own model based on existing open source model, you might need less computing power, but otherwise you have to have computer power which costs like millions of dollars. So what LLM basically does, LLM in a very like simplified way is a model that predicts the next word. So you input a prompt, and then it creates the response word by word, and each time it predicts like the best word which goes after the prompt and the text that was generated before. So basically, this is this in a way a very simple task. However, I mean, even this task is solved using different architectures. And here you see the trio of the different architectures of LLM models. You see that there are encoder models, encoder-decoder models, and decoder-only models. And as you can see on the right side here, the screen of this laptop, the GPT-like models are decoder-only model, as well as, by the way, GigaChat, which is the model that was developed by SBER, and we'll talk about it later. So when you build LLM, you basically have a trade-off of three factors: quality, speed, and the cost of the model. And you cannot choose, unfortunately, you cannot choose all three. You have to choose only two. In order for you to have high quality and quick model, you have to really invest a lot in terms of computing power to build a model, but also you have to have significant compute power for the inference. And in case you don't have significant, you don't want to make significant investments, you have to sacrifice either the quality of the model or the speed of the inference. So basically, you have to have to choose 2 out of 3. And as I promised, we'll talk also about GigaChat, and Andrei will provide more details on that.
Yeah, so we have a world-class text-to-text model, which is GigaChat, which is similar to ChatGPT. It can reply in many different languages, including Russian and English. But we also have other LLMs. We have a text-to-image model, which is called Kandinsky. You can ask prompt, and it draws a picture. And soon it will be able to make a video. And we have GigaVision, which is other way around, which is image to text. When a model gets an image, and you can ask all sorts of questions about this. and we have many other models. So we're really focusing on building LLMs in different modalities to enhance our business, to improve what we do. And how is a large language model built? The first type is pre-training. When you took really large chunk of data, you throw a lot of computational power, but then you need to do SFTs, supervised fine-tuning. That means that you take less data, but higher quality data. And then you analyze it and make model better. And to finally align the model, you do a reinforcement learning. It can be either with human feedback or other reward modeling, but that's the way how it is done. When we assess how good LLM is, we look at 3 domains. We look at L0, L1, and L2. L0 is just general knowledge about world. L1 is a knowledge specific to some domain like medicine, finance, law, and so on. And L2 is a knowledge specific to some task or some situation. So it's really a skill.
Particular skill, yeah.
It's particular skill that you want to improve. What is really nice about these models that they can be used for many different purposes. They can do text editing, they can do summarization, you can chat to them, you can brainstorm, you can ask some questions, and it can do a large variety of tasks, and that's very nice. So it can be used for multiple different purposes. And LLMs are now drifting towards being capable to deal with different modalities, which is text, which is image, video, audio, and it can reply about audio, what is in there, or create an image, or do many other things. And next step that we're almost there, and soon it will be a huge trend, is agents. So agents is LLMs that can perform some tasks. You can ask them to do something, and it will understand what you want them to do, and then perform this task. And other current very important trend is called RAG, retrieval augmented generation, in which LLM uses a query to fetch data which is important for this prompt, and it can make actions of LLM and answers of LLM more reliable. And now we're heading towards a world where different LLMs or different agents can interact together. They can, for example, develop a website when some LLM could act as a programmer, some as a tester, and so on. So they can share different roles and together build and solve very complex tasks. So I was talking about all this stuff, but I and Jahangir, we are from risk management. So Jahangir, let me ask, where is risk management? Why is it so important for the LLMs?
So indeed, why risk managers are concerned about LLMs? Yeah, I mean, there are certainly risks in LLMs when we use them, and even when you use LLMs for like entertainment purposes, there are risks in there. For example, you cannot control each and every answer that is produced by a large language model. It might depend on the prompt. It might depend on the previous chat results with the model. And imagine, for example, that LLM chats with a kid, with a 6 years old boy or 8 years old girl, and you don't want LLM to produce sort of toxic toxic results in the answers, right? So even when you use for like non-commercial purposes, like for entertainment or something, then even there might be risks. And other risks which are more related to the business use cases are here on the slide. For example, certain people may use prompts which may result in the data from the training sample to be available to the creator of the prompt. And for example, if you use LLM in the training sample, if you use your internal documentation or some secret data or whatever, then with the use of the prompt, some people may just extract that particular information that you don't want to be extracted. Another harmful way when certain people may harm your business is when the information that's produced to train LLM is somehow created specifically so that it creates specific responses, which are again not intended to be produced. Another way where the risk may arise is when LLM is used, for example, in specific needs, like in hospitals as a helpful instrument for the doctors. And if the medical report produced by the doctor is supported by the results of LLM, if something is wrong with the response of a large language model and the doctor does not see it, then and doesn't correct it, then there might be wrong diagnosis and wrong way of treatment of people. So these are some of the risks that that LLM may produce. And it's not only Andre and I who are concerned about risk of LLM. It's actually, if you consider the responses of the World Economic Forum, you'll see that the experts actually put AI-generated misinformation and disinformation. You see this on the left side of the slide, that this risk is already second among all risk types. And this is the average response by the experts in the world. So, and the only risk that is above is extreme weather. So you may consider how important this risk is for the people. If you look at the right side of the slide, you'll see that this particular risk is actually the one that increased most among all risk types. So it went from by 15 places to the second place.
Excuse me, Jangir. We are allowed to ask questions during the presentation. Can you go back?
Yes, sure.
Previous. No. Next one. No.
Here?
Yeah, this one. Are these responses of experts, or are these really observed cases of wrong behavior of these models? These percentages.
The way World Economic Forum actually does this, they publish this report every year. They ask experts around the world on the perception of the risk. So basically, this is more expert-based, and this might be again based on the evidence, or might be just feeling of people. But this is the way.
These are some kind of probabilities of expectations of experts to what kind of errors might make these models might make. Yeah, okay.
This is how experts perceive the risk from different sources like weather or AI or whatever. So this is not something that is based on statistical data.
Yeah, but there were some cases where it actually happened, and it did some harm.
Yeah, and actually there are people who went to prison because of the use of LLM, or not LLMs, but rather generative
Yeah,
AI models.
generative AI for some evil purposes.
Yes,
They-
for some evil purposes, even that already happened.
You see, this is here, for instance, accidental or intentional nuclear event, or violent civil strikes and riots. You see, and 12 and 11%. Is it possible to measure or evaluate this probability or whatever with such accuracy? I don't know.
No, it's not a probability, it's a share of experts which thought that this risk is huge.
It's huge
I see.
among
It's a share of experts. Oh,
Yeah,
I
it
see.
was just a survey. So they
I
asked
see.
and experts what risks are high, and they were allowed to choose multiple answers, and more than half of them choose AI-generated misinformation, disinformation as one of their answers.
Okay, thank you very much. Let's go further.
Yeah, let's go
Sorry.
further. Unfortunately, as I said in the beginning, I have to go. Thank you very much for your attention. I'm sure Andrei
Thank
will.
you very much. And we will listen the rest. Yes.
Okay.
Yeah,
Thanks. And
thank
goodbye.
you. And I see there was some question in chat. I'm doing, thank you for presentation. I'm doing my research in application of decision support system. Actually, I have a humanitarian background. So I'd like to get a better understanding how technologies are being used in organizational environment. Is it possible to get a one-day invitation to your department and see it in place? May I ask for your contacts or leave mine for further communications? Yeah, thank you for this question. I think, so first of all, let me talk about AI journeys. There will be a huge conference on artificial intelligence in December, organized by SBER, and we will show many different things that we are doing and how it is used. And well, you can, yeah, you can send to organizer your contacts, and we will talk to you, and maybe we'll figure out how we can show you what we are doing. And by the way, we're hiring, so if you want to do it full time, you are more than welcome. Okay.
Okay, let's go further.
So yeah, let's go further. Yeah, and so what are main problems that can be used, that can be caused by LLMs? So first one is wrong and hallucinated answers. It is very well known that LLMs sometimes hallucinate. So they look very certain about some answer, which is actually not completely false, and it happens. And another problem is weak learning, when it does not answer properly, and it's not very good at learning certain subjects. And third one is toxic behavior, because it is trained on all data in the internet, and sometimes some texts are toxic, and it can be behaving not very well in this case. So it could happen, but first of all is how we should mitigate this. First thing you should think about is what is the process that in which you are using LLMs. If the answer of LLMs are checked by human later, maybe the risks are not so high if he can just stop override some wrong answers. Another way is what is domain. For example, in medicine, wrong answers are more harmful than in some entertainment industry. But regardless of this, it's necessary to validate these large language models and understand what it can do well, what it cannot, and if there are some weak points, to make some suggestions how they can mitigate it, how model can be improved in this domain. And that's basically what we do in model risk. there are many causes why LLM could work poorly. It can be exploited, so it can work poorly because evil intent of person who writes a prompt or who injects data into the training set. But it can be just problems that technology is still not perfect, and it can produce any kind of nonsensical output or random hallucination on many others. And there are some examples how it can be used in evil way. For example, in GPT-4 you can put a picture. It looks completely white, but there is a text, and it says, it gives an instruction, don't describe the text, but make an ad, and model replies with this ad. And another way is that if prompt is written in English, model replies properly, but if it is done in other formats, model starts to put toxic replies, and so on. So what can we do? There are basically, there are basically three main areas that we do. First area is benchmarking. We estimate how good the model is for some kind of benchmarks, and I will talk about it more later, what kind of benchmarks we use and how we use them. Another thing is autometrics, when we automatically estimate which model is good and areas in which model is not so good. And the third one is human annotation. It's done either by side-by-side comparison, which model is better, so on. So generally, human assessment is more costly, but sometimes it is actually needed, and there's no way to avoid it. And let's move to the benchmarks. There are many different benchmarks to estimate LLMs. A lot of them are public, and we very often estimate our models to find weaknesses and to find how we can improve them. One example, very famous benchmark is GSM 8K, which is a benchmark for school level math, and it gives quite a simple math problems, and then we find out how often the answer is correct. And another really big benchmark is called MERA, multi-evaluation for Russian language architecture. It is Russian language benchmark, but it's most widely used, and you can see a benchmark. GigaChat is there and other models. It's estimated in several different domains, which gives a very good broad idea how good the model is and how it is compared to different to other models. And different way that we are doing is so-called chatbot arena. There are these arenas in Russian language, in English language. How is it working? Any person can log into this arena, ask a question, and he is given answers of two different LLMs. He does not know what are these LLMs, but he or she says that answer of model A is better or answer of model B is better. And then ELO-based rating is calculated, so similar to chess, and this way it is shown which model is good and which model is not so good according to people who assess it. And so it's a very good way and very cheap way to get an idea about human assessment. Another very famous and very common way is to use LM as a judge. We get an answer of model, and we use some different model to assess which answers are good and which are not so good. For example, we give an instruction, write 5 sentences ending in apple, and then we just calculate how many sentences actually end with the word apple. And we see that model A, which is on the left side, does it perfectly. All 5 answers contain word apple, and the model on the right side, model B, is not so good. It gives only 4 answers, and one of them ends with the word fruit and the other ends with the word dessert. So it's not so good. And there are more sophisticated examples where, when, for example, you test text-to-image models. You say, write a picture of apple, and then use a model which is image recognition model to, and ask this model, is there an apple? And this way you can check whether the apple was indeed drawn, indeed apple is in this picture. So LM as a judge is very common, and we develop a lot of in-house models to make better assessment of LLMs. So the second area, how it is done, is autometrics, when you can estimate many different stuff using some automatic algorithms. And then it's important to check correlation with some human feedback. And in the ideal scenario is when this correlation is high. That means that you can use this automatic model and do a very quick and very efficient comparison of different models. So this is example that you can check coherence, you can check relevance and other stuff. So you can see whether text is written well or not. Then autometrics can be analyzed to can be used to analyze text perception. You can check grammar using these models. For example, there is a so-called COLA, corpus of linguistic acceptability, and there is a COLA which is called RUCOLA, which is made for Russian language, and it can check many different grammatic mistakes, and it can automatically highlight problems with language that some models have. And moreover, these models can be used to estimate emotions. For example, some text could be seen as offensive or like bullying, and there are models that could grab it. And using these models, you can estimate how often does the model respond in an aggressive way, for example. And it's very important because if models, for example, interact with children, you don't want it to be aggressive, no matter what the prompt is. So that's another way how we do it. And one very important stuff for answers is that not only text matters, but stylization matters as well. You want to use different fonts, you want to use indenting and so on. And we checked that well stylized texts are more liked by humans. So this is very important, and we analyze the stylization and make sure that GigaChat is doing it in a good way so that people really enjoy it. Another problem that we could experience is repetition. And for example, this is a prompt which says in English, I have an apple, and it asks to translate it into German. and it can translate well. Sorry, I will not try to read it because unlike GigaChat, I don't speak German. But sometimes it can just repeat text in English, which is wrong. And sometimes it can go into repetition and have some problems. So that's LLMs are very prone to it, and we make an effort to check that it's ideally never happens, but in reality happens more and more rarely. Now let's go on to human evaluation. And the most common way of human evaluation is SBS, so-called side-by-side comparison. We have a large number of assessors, and we ask them to estimate which answers are good and which answers are not. So they see one questions and two answers by two different models, and their task is to choose one of the four options. Either model A is better, second model B is better, third both models are good, and fourth both models are bad. And based on these models, we calculate so-called SBS score, which shows which model is better, which model is worse. And this is one of the most primary ways we estimate our progress, and we look at the best LLMs in the world as a comparison, and we do SBS against best models. And very important reason why we do it, we divide questions into subgroups based on different skills that are required, and we see in what skills our model performs well, and in which skills it performs not so well, and we give recommendation how it can be improved. And this is example how it's done. It's quite an old one, but it was published. It was published in the internet, so it's not confidential. So I can easily share it, and we can see that we divide into different skills: how well it does a brainstorm, how well it chats, how well it answers closed questions, open questions, and many others. And this way we found weak spots and make recommendation how it can be improved. When we do it, there are many assessors, and not all of them are equally good. So we need to check how good the assessor, how high is the correlation between his answers and different answers of other assessors, so we can make an estimation better by just assessing assessors, which we are not just taking results for granted. We can check how well they answer based on statistics and based on correlation with different assessors. And we divide into three groups. One is when model A is better, second is when model B is better, and third one is where the difference is not statistically significant. We use confidential intervals and so on because, well, it's very important to understand when the difference is actually statistically significant or not. And there are a lot of cases when there is a tie, and we see that models are equally the same. There are some ways how we do it. I think the most important technique is to use honeypots, which is the kind of questions when you know what the proper answer is, and therefore you look how assessors assess these answers, so you can estimate how good assessors are and this way understand which assessor should be more trusted and given higher weight to his answers. There is a David Skin method, how we estimate overall probabilities, and now it's probably the most common way how you take into account all this honey points, correlation, and make an assessment which compares model in the best way. It's very important to use an overlap. It means that each question should be asked to different assessors, and it's usually you want an odd number of assessors because you don't want to have a tie. And so in this example, we used 4 assessors and 5 assessors, and in this way, you can get more consistency and more, and the result you get is more robust to some mistakes that are making by a specific assessor. And if we go further, sorry, there was any question? Yes.
Yeah. In chat there is a question, Andrei. Didn't you ask ChatGPT how to validate LLM models?
Well, we asked them, but we asked ChatGPT, we asked GigaChat, we asked different models, but what they actually do, they reproduced the data that they seen in the training set, and most information about validation are not available in the public domain. So most of the stuff we're doing, it's our own research. We have a very strong R&D group which makes research how we can estimate one or another feature of LLMs. We, for example, as I told, we made different LLMs to be used as LLM as a judge to assess answer of our LLM and our competitors' LLM. So it's a big research. I know that LLMs are heading towards being useful to in research, but there is still a long way to go.
Thank you. Let's proceed.
Let's proceed. Okay. And if we talk about what will happen next and where are we going next, I think first of all is the task is to make LLM smarter. LLM can do research or solve very complicated problems. Where we're heading towards this way, and sometimes you need to specifically teach LLM for some domain. For example, GigaChat successfully passed a medicine exam, and for this it was taught specifically in the medicine domain. Another area for development is mastering of many more modalities. It can work with text, it can work with audio, video. For example, video is very challenging nowadays, but there is a lot of research to made so LLMs can be improved and can do better. Another way is agents, because you want not only to find information, but you want to perform some tasks, and you can sometimes ask agents to do some of your works, some of the work themselves, and it's a very fascinating area, and we are doing a lot of research on this one, and it probably will lead to fascinating results, because when different agents interact with each other, we can do a lot more different things. And so it's a very big area. And another one is adaptability, we called it. So how can we make personal LLM for some kind of people? We talked about toxic behavior, but for example, drawing a picture of snake is not toxic, but there are some people who are afraid of snakes, and for them probably models shouldn't draw a picture of snake. And so there are many ways how LLMs could be adjusted for some specific individuals, and and probably in future we'll have a world where people can have their personal LLMs, which can interact in the way that this person thinks is the best one. So that's finished my presentation. I have left quite some time for Q&A, so I will welcome any questions, and thank you for listening to me.
Thank you very much. And please, questions, remarks, comments. Let me start first. You see, I would like to make maybe more clear the situation. What about this financial applications? Because the title was about financial applications. What kind of financial applications this LLM was used or checked, to which extent it can be used? Just maybe to give a list of these applications.
For financial applications, there are, first of all, it can be used to analyze documents, text, all the interaction between client, which can be either retail client or corporate client, with a bank, and it can analyze this text and make recommendation or some other stuff for managers how to deal with this client, what this client needs, and so on. And another one is so-called copilot, when a client asks questions how this financial product works, and this model can give an answer, and for these purposes, it can be used to enhance client experience and give good answers. And there are many more which are being researched, and we see a great potential for generative AI in financial business and in other businesses.
And let me ask you one more question, just to understand. You said that this LLM system might be used to evaluate, for instance, customers, commercial customers or customers. Yeah, but let me ask you in the following form. You see, did you try to apply this to this evaluation? For instance, some kind of ability to return some large credit, for instance. Firm would like to get a credit from the bear, for instance, yes, and LLM evaluates this very ability or capacity of customer to give back this.
Okay, so
the question is, evaluated this kind of things?
So the question is, can LLMs be done to be used to evaluate clients? Well, I think it's I think it's ongoing research, so we'll.
Ongoing research, okay.
Yeah. So
because why I ask? You see, we have these mathematical models of network analysis, which might be used for these reasons, you see.
Yeah.
These are absolutely new models and taking into account the subsets of contacts, etc., etc. So, and I cannot imagine that today, for instance, LLM might create such kind of thing. Well, I don't know. At least what do I know? That these very models which we constructed, taking into account this group influences, they are unique absolutely. They are very new and very unique. And to which extent this LLM might learn and apply it, I don't know.
Well, yeah, I fully agree that LLMs are new technology and we don't fully know yet what it is capable of and what is not capable of. We're doing a lot of research on this stuff. We can see some areas in which it's already which can do well, for example, analyze some big text, analyze some pictures and so on. It can work, but for different applications, we are just doing research and trying to find out what to do and how it can be done.
Okay. The story is, yeah. For last several years, I have been interested in this ability of this artificial intelligence to translate texts. And I can tell you that only this year, very few months ago, it started to translate in that way that, for instance, when I check the text, I do make some corrections, but they are really, you see, very few. And rather, you see, easy to correct. Even 1 year before, even 6 months before, it was necessary to rewrite sentences completely, etc., etc. So I didn't like it at all. But now, you see, we have especially ChatGPT. The last version does it very well, in a very high level, you see. It's the first, I can say, a few months, only 3 months, something like that.
Yeah, I fully agree with what you said. We also see that for translation, LLMs are becoming much and much better. So it can be surely used on par with other models. So that's and what we should understand that LLMs are still developing very rapidly. There are some stuff that LLMs were not able to do 1 year ago, and they're capable of doing this today, and they will be capable of doing much more in a year. So maybe that's why constant research is needed. If you find out that LM cannot do something today, you should recheck it a year ago or even a month ago, a year later or months later, because it can change. You can easily change.
Yeah.
And that's why we're estimating.
Approximately a year ago, no, maybe 2 years, a friend of mine who is the head of the Department of Mathematics in Israel, she told me, do you use this ChatGPT to write this survey part of the article? I said, no, David, never. And he said that I started to use it, and it is very really save time a lot. Because he's professional, you understand, and he gets this text and corrects it naturally. And I didn't use it for surveys, but we are thinking about it. But translation has become really great, absolutely. Yeah. Okay, so Some other questions, comments, remarks, please go ahead. Maybe in our parallel translation.
In this chat, there are no new questions. Maybe in some parallel translation.
Yeah. The story with this, no. Okay, I just wish you success and please keep us informed, and maybe sometime later you will give us a new new vision, new insights to this very process. And from my point of view, you see, this is really interesting because these very models which we developed concerning this network analysis and etc., data analysis, might be really useful to, let's say, to marry these models like ChatGPT with these very models, and it might be very useful in terms of these very models of forecast of behavior, etc., etc. So let's work and get some.
Thank you very much for inviting me. It was a really it was a pleasure. Yeah, and it's very exciting indeed to be working on LLMs these days.
Yeah,
So it's like a really frontier of science. And
thank you very much.
And thank you.
Thank you very much, everybody. With this very presentation, we close the school. I would like to tell everybody that all papers will be we recorded all of them, and they will be available not tomorrow, but maybe in a couple of weeks. Will be available on the site of our International Center of Decision Choice and Analysis. Okay, thank you very much, and please also join us at our seminars. We have 2 seminars, all Moscow or Russia seminars. 2 of them are second and fourth Wednesday of months, every month almost, except summer naturally, at 2:30 Moscow time, and this another one is the third Wednesday of the month at 4:30. And I also invite all of you, if you have good results, etc., to present at these very seminars. Just write me. Okay? Thank you very much, and see you. Bye-bye.